Hello, everyone. My name is Lior, and today I'll be talking to you all about NFT authentication, along with my partners, Jack and Ben. So to begin with a bit of background, in late 2017, there was a site launched called CryptoKitties. You might have heard of it. It received a lot of attention almost immediately. It allowed users to trade and purchase these digital cats, which each had unique statistics. And you could also breed these cats together to create new ones. There was a lot of excitement about the release of this site. There was over $1 million of sales in the first week, and some individual cats fetched prices of over $100,000. The reason that people were willing to pay so much for these digital cats is that the ownership was tracked using NFTs, or non-fungible tokens. So what exactly are non-fungible tokens? Well, they're issued on popular blockchains, such as Ethereum or Flow, but unlike cryptocurrencies, every NFT is distinct, and they're not designed to be freely exchangeable. So to give a real-world analog, imagine that you have a US dollar, and so does your friend. You would be happy to exchange that dollar with your friend because the use of those $2 is exactly the same. You can redeem them for the exact same reward at any store in the United States. Bitcoin works the same way. If you have one Bitcoin in your wallet and someone else has one Bitcoin in their wallet, there's no difference between those two tokens. But not all real-world goods work this way. So imagine that you have a ticket to a concert that you're very excited about. You might not be willing to exchange that ticket for one ticket to a different concert, or even another ticket to the same concert that has a less desirable seat. Similarly, you wouldn't be willing to exchange your CryptoKitty for another CryptoKitty that you perceive as having worse statistics. And for that reason, we call it a non-fungible good. Now, how exactly are these tokens implemented? Well, every single token roughly has an address, which is a unique identifier of that token. The token has an owner, and the token also has associated metadata. Now, what's important to remember is that this metadata is not standardized, and there's no particular format that it always follows. But distributed apps generally know how to interpret metadata for a particular class of non-fungible tokens. So for example, the CryptoKitty website was able to read the metadata stored on CryptoKitty tokens. So there's an example of some CryptoKitties metadata on screen right now. You can see it has a name, it has some statistics about the cat, and it might also link to an image of that cat, which is then displayed on the website. Now, how are NFTs used today? Well, they're used for collecting. There's a site created by the NBA, which allows people to purchase NFTs representing essentially trading cards or clips from NBA games. They're used for gambling. There's a site very similar to CryptoKitties that lets people purchase digital horses and bet on their races. And most importantly, and most commonly, they're used for minting artwork. So digital art is very different from physical artwork in that it's very, very easy to copy and reproduce. There's nothing stopping me from you screenshotting your screen right now and copying this image that I'm showing to you. But NFTs allow for creators to distinguish certain users as legitimate owners of that artwork. And actually, there was an NFT sold that transferred ownership of the artwork you're seeing on screen right now for over $60 million. Now, what exactly is the problem with this system? Well, there's a few things that do make NFTs great. One is that ownership is public and verifiable, so anyone can look up the owner of that piece of art I just showed you. And this record is just as secure as the primary currency running on that blockchain. So any image NFT stored on the Ethereum blockchain is just as secure as Ether itself. Also, the associated metadata is immutable, so no one can change the claim made about that NFT after it is minted. However, these NFTs are not perfect. Any user can mint an NFT with arbitrary metadata. So there's nothing stopping me, for example, of also minting an NFT representing that piece of art I showed you. Legitimacy is not well defined either. So just to see this more concretely, imagine that we have an NFT of the Mona Lisa minted by Leonardo da Vinci. I doubt that anyone's going to have a problem with that. He's legitimately the artist who created that piece of work, so it seems like he has the right to mint an NFT of it. But imagine that another user, Ben Bitdiddle, comes along and also mints an NFT for the Mona Lisa. Well, now there's two claims, both which attempt to show ownership for the same piece of art. There's a conflict here. And right now it might be very easy to resolve. We just say Leonardo da Vinci is a legitimate artist and Ben Bitdiddle is not, so Ben Bitdiddle's NFT is false, it is a fake. But what if Ben Bitdiddle modified Leonardo's artwork in some way? Then what is legitimate? This question of authentication is currently answered through use of trusted marketplaces. So it's assumed when people purchase from these marketplaces that the market has done research beforehand and will not sell anything that is not created by a legitimate artist who actually has rights for that work. This has a few problems. One is that this is a very centralized method of decision-making, which runs against the spirit of using this distributed token in the first place. There's also a conflict of interest because marketplaces might be incentivized to label works as legitimate that they want to sell. And authenticity in the real world is non-binary. So you imagine that there's a work of physical art, let's say a photograph, that has an original print, limited prints, and further reproductions. And depending on the context, each of these might be considered legitimate or authentic versions of that piece of art. And there's no way to represent that granularity through the simple fact that a trusted market is selling an NFT. So our goal today is to propose a programmatic relationship between dedicated authenticators and end users, which is sufficiently abstract to handle a variety of use cases, which we see in the real world. We also propose means of programmatic authentication, which is reasonable to use in several, but not all of those use cases.
For our authentication system, we want to move away from the centralized approach that are currently used to verify NFTs. And to do this, we will identify 3 roles that users on our system might have, which are people who wish to sell NFTs, those that verify those NFTs, and those that wish to buy NFTs. So our system might have several sellers, authenticators, and buyers. But let's just consider the perspective of a single buyer wishing to buy NFTs. And now the goal of these sellers is to get their NFTs verified by these authenticators. So let's say seller number 1 reaches out to authenticator number 2 and gets their NFT verified. And seller number 2 is then verified by, say, authenticators 2 and 3. And now, if a buyer wishes to buy these NFTs, they had to specify which authenticators they trust. So let's say this buyer trusts authenticators 1 and 3. And then to decide whether or not a NFT is legitimate, the buyer then goes to the NFT and checks to see if it has been verified by an authenticator that it trusts. So as you can see from this graph, the buyer should trust NFT number 2 because it was verified by authenticator number 3, which it trusts. But now, how does these authenticators actually go about verifying these NFTs? This is our second goal, which we'll solve by using a chain of authentication methods, ranging from automatic machine perceptual hashing, which we'll explain later, all the way to manual curation via the form of expert reviews. And the reasoning behind this chain going from automatic to manual is because we believe that most disputes can be resolved automatically. Most modifications to artwork are very simple, things like cropping or changing the color of the image, which can be done with machine vision and just resolved without the need for a manual review of artwork, which can be very time consuming.
So the first method we'll talk about is perceptual hashing. So with the normal cryptographic hash, it's a function that takes an input and maps it to a random hash value in a way that if you were to modify the input slightly, it'll give you a drastically different output hash value. With the perceptual hash, if you were to modify the input slightly, it'll still give you a pretty similar hash output value. And depending on the algorithm that you use, this could be resistant to things like resizing an image, rotating an image, or minor edits like compression artifacts from updating an image. So as an example, I have 2 images here on the left. One is the original Peacemaker image, and the second one is a copy of it where I boosted the brightness and then added a red border. So first I computed the hash value of both of these images, which gives me a vector of numbers. And then I computed the cross correlation of the 2 vectors, which gives me something pretty close to 1, which means that it's very likely the 2 input images were very similar or derived from one another. In contrast, if we looked at the same approach, but with 2 unrelated images, we get a correlation that is close to 0, which means that the 2 images were likely unrelated and completely different. So in the context of NFTs, this is useful for us in that whenever a new piece of art is published, a authenticator can go in and compute the perceptual hash of that new image and then compare it to the hash values of existing published artworks to see if it was a derivative of one of the existing artworks. So the advantages of this approach is that it's very fast, it's automatic, and we can make the algorithm more robust by using multiple perceptual hash algorithms that look for different features of the image when computing the hash. Of course, there's drawbacks in that if the new image is a heavily modified derivative artwork of the original one, then the hash algorithm might not be able to see that their hash values are correlated. And this is also vulnerable to adversarial example attacks, where if the adversary knew how these hash functions worked, they'll be able to generate new images that are very similar to the original image, but give you a completely different perceptual hash value. So to cover the cases where perceptual hash in these automatic schemes fell, we also recommend authenticators to use crowd worker voting to decide if a new artwork is a derivative work. So this involves using a system like Mechanical Turk and asking human crowd workers if a new piece of artwork is a copy or a parody of another existing artwork. And we imagine this would be useful in a case when artworks have been heavily modified or there's special licensing laws that allow people to make parodies of original artworks. And of course, if all else fails, we can always consult experts or specific art curators, which is basically what the current NFT marketplaces are already doing. Of course, this is usually pretty expensive since you're consulting experts. And this will only make the most sense if you're working with artwork that is very expensive or will likely return a lot of money on the marketplace. So in conclusion, using this chain of authentication methods, we allow authenticators to be able to pick and choose what methods work for them for their specific verification case and specific cost considerations. So, well, thank you for coming to our talk, and want to thank the course staff for the guidance on this project. And we'll be happy to take any questions.